In this video, we're going to look at some more related rates problems. In this problem, a conical paper cup is 30 centimeters tall with a radius of 10 centimeters. The cup is being filled with water, so we're adding volume to it so that the water level rises at a rate of 3 centimeters per second. At what rate is the water being poured into the cup when the water level is 4 centimeters? So we'll go ahead and draw a little picture to help us out. Here's our cone. We have a certain height and a certain radius. They do give me those measurements for the total, height being 30 and total being 10. They do want me to find dV/dt. How much is the volume changing? How fast am I pouring water into this? A couple pieces of information they did give me. dH/dt is 3 centimeters per second and h is 4 centimeters. So the rate of change of the height is changing at a rate of 3, and then they want me to freeze it right at the height equaling 4. So the volume formula for a cone is 1/3 pi r squared h. The problem with this one is it has a couple variables. It's got, on the right side, it's got the radius and it's got the height. And instead of doing the product rule, that could be kind of cumbersome. So a better way to do it is to try to substitute one of those variables out if we can. We know the height is 30 and the radius is 10, and we're trying to freeze it right when it's 4. Now we do have similar triangles. So this oops, wrong button. So this triangle right here is similar to this triangle right here. So I could do a proportion or some kind of scaling factor for all of those. So we're going to go ahead and do that. I'm going to say that the radius is the height divided by 3. So if I know the height is 30, I can plug a 30 right in for that h right there. 30 divided by 3 is 10, so that matches up with my radius. So I'm going to use that. I'm going to substitute that in for the r. That way I have an equation with the volume equaling all h's is my goal. So I can use my dH/dt and my h. So I'll plug that in, 1/3 pi, and then instead of r, I'm putting h over 3 squared and then multiply by h. And then we're going to simplify that. So we're going to square the h over 3 out. So we're going to have the over 3 right here being squared is 9. And then we already have a 3 right there. So we should get 1/27 pi and then h cubed. The reason it's h cubed is because we do have an h being squared and then we have another h right here. So those combined would be h cubed. So that's my main function. Now I can find the derivative of that for my related rates function. So I'm going to derive that with respect to t. So dV/dt will equal, really the 1/27 pi is a constant. I'm really just taking the derivative of h to the third. So power rule that. 3 goes in the front and drop it by a power. Variables don't match, so I do need to tack on this extra dH/dt for my chain rule. So we're good there, and so now we can just replace h with 4, and we can do dh, replace that with 3 on this problem, and my dV/dt would end up simplifying to 3/27, 1/9 pi, square the 4, multiply it by the 3, so my change in volume simplified should be 16 pi over 3 centimeters cubed per second. The units is volume changing, so that's why it's centimeters cubed, and then per second because it is a rate of change. So that's how I would attack that one. All right, so next problem, another cone. So we have a conical paper cup. It's 20 centimeters tall with a radius of 10 this time. The cup is being filled with water at a rate of 2 pi over 3 centimeters cubed per second. How fast is the water level rising when the water level is 4 centimeters? So this one, they give me the dV/dt, and they want me to find dH/dt. So we're going to go ahead and draw a picture. There's my height and my radius. How fast is the water level rising? So that is dH/dt. How fast is the height increasing? They do give me dV/dt. That's going to be the 2 pi over 3. And then they also give me the height. Once again, freezing it at the height equals 4, and so that's when we're pausing this to see how fast it's moving at that moment. So our main formula again, 1/3 pi r squared h. This time the radius is 10 and the height is 20. I still want to come up with a ratio or proportion that will simplify or get rid of one of those variables for me. So on this one, I would say r is h over 2. So if I plugged in a 20 in for that h right there, so the height 20 divided by 2 would be 10, so that would match up with my radius. So I'll plug that in for my radius in my formula, 1/3 pi h over 2 squared, that's my r, and simplify similar to the last one. So square the h over 2, that'd be h squared over 4, and then condense my like terms. So I get 1/12 pi h cubed. Now we'll go ahead and take the derivative of that with respect to t. So dv dt, the 3 would move in the front, simplifying 3 over 12 is 1/4, and then pi h squared, dropping it by power, and then dh dt because of the chain rule. Once I have my related rates formula, I can plug in my 2 pi over 3. That is my volume, so I'm going to plug that in for the dv dt, and then I'm going to plug a 4 in for the h. So 2 pi over 3 equals 1/4 pi 4 centimeters squared, and then dh dt. And I do want to solve for dh dt. I just have to divide by all of those the simplified numbers. So the 1/4, 4 squared would be 16, and then I can cancel out the 1/4 to get 4 pi, and I divide on both sides. So I get 1/6 centimeter for my dh dt. And that should be centimeters per second. So I got to sneak that in there. Centimeters per second for this one. All right, cool. So that's that one. So the next one is we're getting away from cones a little bit. So we have a 17-foot ladder leaning against a wall. It is sliding towards the floor. So the foot of the ladder is sliding away, and so basically the ladder is like slide falling. So how fast is the top of the ladder sliding down the wall when the ladder is 8 feet from the ground? So let's go ahead and draw a quick picture of this. I've got my building, I've got my 17-foot ladder leaned up against it, and it's sliding away. So I've got a couple variables I can throw. The base, or the distance on the ground, I'm going to call x. The distance on the height of the building, I'm going to call y. You could pick any letters you want. And they want to know how fast is the top of the ladder sliding down on this one. So if I were using, like, what did they give me? They gave me the 4 feet per second. That's dx dt. That's how fast the x value is changing. I don't know exactly what the x value is at that particular moment. They do tell me that we're pausing this when the ladder is 8 feet from the ground. So y will equal 8 feet at that given moment, at that freeze frame moment. So I need an equation that will connect x, y, and 17. And so we'll just use the Pythagorean theorem for that. So x squared plus y squared equals 17 squared for my Pythagorean theorem. Now I could use that equation to solve for x at the moment that I'm freezing it. I might need it, I might not, but I'm going to go ahead and solve for it on this one. So x squared plus 8 squared equals 17 squared. And if I just solve for x, I should get 15. So right when it's 8 feet from the top, it'll be 15 on the ground. But that's just a static equation. There's no related rates on that. So now we're going to find the derivative and see what we get there. So derivative with respect to t, 2x dx dt plus 2y dy dt, and then it equals 17 squared is a constant, and so the derivative of that would just be 0. So I'm going to plug in my values. I know my x value is 15, dx dt is 4, the y value is 8, and I'm solving for dy dt. So I'll throw all of those numbers in my formula and simplify. So I get 120 on the left, 16 dy dt, or on the second part of that, equals 0, and I'll solve for the dy dt. So I'll subtract 120 and divide by 16. So my dy dt should equal negative 120 over 16, and of course we can just reduce that just a little bit. So I get negative 15 over 2, and that's going to be feet per second. Now that rate is negative because the ladder is falling down, right? So it's the y value is getting smaller, and so it's going to have a negative rate of change. It's changing the height in a negative direction, so it's got to have a negative rate for that one. So that's how I would attack that one. On this one, we have a 6-foot tall person walking towards a 19-foot lamp post at a rate of 6 feet per second. Assume we can draw the scenario with right triangles. At what rate is the length of the person's shadow changing when the person is 15 feet from the lamp post? So let's draw a picture of this. We got our lamp post that's 19 feet tall, and then the person is 6 feet tall, and they're walking towards that lamp post. So I'm going to throw a couple variables on there. I'm going to say x is my shadow length, y is the distance from me to the pole, and they want me to find out how fast the length of the shadow is changing, so that's dx dt. It's the change in x where my shadow is. Dy dt, they tell me is how fast we're moving. Now that one we're moving at a rate of 6 feet per second. I am walking towards the lamppost, so the y value is getting smaller. So since the y value is decreasing, we should have a negative rate of change. That's why I put a negative on the negative feet per second on this one. The 19 feet, 6 feet, those are both constant throughout the whole problem. The 15 feet is specifically the length or how far away I am or the person is from the lamppost. That will be changing, but I'm freezing it right at 15. X I don't know. I'm not going to solve for it quite yet. I'm going to try to come up with an equation that will connect those. I can't really use Pythagorean theorem on this one. However, I do have a couple similar triangles in there. So to help you see that, let's go ahead and separate that smaller triangle. So I do have two different triangles, the 6 and the X triangle and then the big triangle. So those two are similar to each other. So I can write a proportion between those two. So let's see, the left sides are 6 and 19, so I can connect those. And then the bottom sides, I can say X would relate to the whole bottom side on the big triangle, or X plus Y. So I'm going to write the proportion, 6 over 19 equals X over X plus Y. So I'm connecting those two triangles with a proportion. Now I could just do the derivative right here, right now. However, that would not be very easy to do. I'd have to do the quotient rule, and it would be kind of a bear. So it might just be easier to simplify that first. So I'm going to go ahead and cross multiply those two and get 6x plus 6y equals 19x. And that is much easier to deal with in the derivative world. So I'm going to clean that up a little bit further, maybe get some like terms together. So I'm going to go ahead and say 6y equals 13x by subtracting 6x on both sides. And now I can derive both sides. So I'm going to take the derivative with respect to t. 6 dy dt equals 13 dx dt. Now I've got my related rates equation. So one rate connected to the other. So looks like I don't have any x's and y's, so I didn't need to solve for x in this case. I could have, but I don't really need it. It's not in my derivatives. I need a dy dt, which I have, negative 6, and then I'm looking for dx dt. So I'm going to plug in that negative 6 and see what I get. So my dy dt, I divided by 13 first, sorry. Plug in a negative 6 for that, multiply those through, and I would get negative 36 over 13. Of course, units for that one would be feet per second, so that's how fast the length of the shadow is changing on that one. All right, and the last one, we have an observer who stands 400 feet away from a launch pad to watch a rocket launch. Rocket blasts off and maintains a velocity of 500 feet per second, so that's the rate of change for the rocket position. Assume the scenario can be modeled with right triangles. How fast is the observer to the rocket distance changing when the rocket is 300 feet from the ground? So let's go ahead and draw a picture of this. We've got a rocket being launched, and we're an observer standing, looks like 400 feet away, and I'm looking to try to find how fast the observer to rocket distance is. That would be the hypotenuse on this triangle. So I'm going to go ahead and label what I know. So I know it's 400 for the base. That's not changing. I'm not moving closer or farther away. And then the rocket, we're going to call that height y. We're going to call z, the hypotenuse, the distance from the observer to the rocket, and that will change as the rocket flies up. That z is going to get bigger. So they want me to find out what is dz dt, how fast is that changing at what rate, specifically when the rocket is 300 feet from the ground. So dy dt, the change in height of the rocket, is going to be 500 feet per second, and then once again freezing it right at 300 feet for this one. So an equation that would connect this, once again Pythagorean theorem would be a good choice. And on this one, I once again might need that other variable, but let's go ahead and find the derivative first on this with respect to t, and we'll see if I need it. So the 400 squared goes away, it's a constant. 2y, or y squared goes to 2y dy dt, and then similar for the z. So it looks like I will need the y and the z. I have the y. I don't have the z, so I'm going to go ahead and solve for that z using my original Pythagorean theorem, plugging 300 in. So I plug into 300 right there, and I can solve for z. I get z equals 500. So 500 feet is exactly how far away the rocket is at that moment. So I'll go ahead and plug those numbers in. My y value is 300, so I'll put a 300 there. And my dy dt is going to be a 500, so I can plug that in there. I'm going to go ahead and cancel the 2's out on both sides early. You don't have to. You could have left them there. It's fine. And then I'm going to solve for dz dt. So I would divide both sides by 500 again. So it looks like I get 300 feet per second for my dz dt. It's how fast the distance from the person to the rocket is changing.